Hey guys, today we'll be solving LeetCode number 33, search and rotated sorted array. It is a medium question on LeetCode and it is also the daily problem for today. Okay, uh, this is very closely related to the algorithms we applied in the other rotated sorted array questions that have been coming up in the past week or so. I've uploaded them to the channel already. You can attempt those as well. For those who don't know and are picking up, well, starting to watch the channel now, then first I'll explain what rotation actually means. So let's consider an array 0, 1, 2, 3. Okay, we say that this is rotated 0 times essentially. Why? Well, because it's already sorted, right? You see 0, 1, 2, 3, it is in a proper ordering, right? We would consider this to be sorted array. Let's rotate it once, right? Now let's rotate it once. And how does rotation work? You can think of rotation being like a circular thing essentially. When we say rotate 1, it essentially just means shift by 1. So shift everything by 1, and everything that goes out of the array now comes back in from the very start. Okay, so we would have 3, 0, 1, 2. We've essentially just gone full circle once. Rotate 2 would have the same effect. We would now have 2, 3, 0, and 1, right? And that's about it for rotations themselves. The rotations help us in one specific part though. That is, if we were given a rotated 0 array, that would just be a regular sorted array, and we could conduct a binary search on that in O of log n time. We don't really have to worry about those arrays, right? And by the way, I'll be talking about the log n approach because the O of n approach is really straightforward. I'm more so interested in explaining the log n approach. That is the more difficult one. Okay, now let's consider rotated. I'll just start off with a simple example. So let's consider the example 6, 7, 0, 1, 2, 4, and 5. This is a sorted array, right? In the sense that it has been rotated twice actually, right? 6, so it used to be 0, 1, 2, 4, 5, 6, and 7, but now we've rotated it essentially. And let's consider the middle of this, right? Like any other binary search algorithm, let's consider the middle of this. So let's consider 6 by 2, right? 3, index number 3. Let's go to index number 3. Let's look at 1. Okay, let's consider this array now, 6, 7, and so let's consider the two parts of this array. Okay, let's say, well, actually, first thing we can do is we are also given a target, right? Essentially, that's what we're supposed to do. We're supposed to determine whether this target exists or not, right? So let's say the target is some unknown value right now, and the first thing we will do is we will check if nums mid is equal to the target, a very standard check in binary search, right? If it is, then we will simply return mid and be happy about it. But now I'm going to talk about the cases that, you know, in the sense that we will need more than one iteration of binary search to go about it. So 6, 7, and 0, and 1, 2, 4, and 5. How would we go about this question? So let's split the array into the two halves that we would usually with binary search. What do we notice about this? We see that it goes up, 6 and 7 go up, and 0 and 1 go down, and 2, 4, 5 remains sorted as is, whereas this side is now unsorted. Let's consider another example as well. Let's do 2, 4, 5, 7, 0, and 1. And if we split this, 2, 4, 5, 6, 7, 0, and 1. As you can see, this side is sorted, this side is unsorted. And let's consider the example. Let's just consider this example over here. In this case, we would get both as sorted, right? So what did we learn about going through this? Well, at any point in time when we have a middle, right, and we essentially splice the array with the middle, what happens is we can see that it can either be sorted, 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 unsorted, or unsorted, sorted. So there is the fact that both of them are sorted, we are happy with that, no worries. Sorted and unsorted, unsorted and sorted, right? What is the mean, like why, when do we when are we able to conduct a binary search? We're told that it should be a sorted array, right? That is the fundamental basics of a binary search. So when we splice the array, would it be wise to check, well, are both sides sorted, or is one side sorted, or is one other, like which side is sorted is something that we want to see essentially. And that's the whole basis of this question. Once we splice the array, all we want to do is just check, is my left array sorted, is my right array sorted, right? And we want to determine which direction to go into immediately after. So let's consider the standard algorithm now. So we will have our starting point be the starting index and the very last index, right? And let's write out the initial steps for now. So mid is just L plus R fluid, and like I said, if the one that we are sitting at in the middle is actually equal to the target, then we are more than happy to just return middle straight away. There's no worries with that. But now let's consider the case where we'd have to determine which side is sorted and which side is not sorted, and we will operate only on one of them, right? Like I said, if it is sorted on both sides, well, the thing is we can just check whether our target would fit inside this, or would it fit inside this, right? But if we're given a sorted and unsorted, then we would always want to go into this, and we would again check for target. If target would be in these bounds, that's when we would go into that. Okay, I'll write this out in code so that it's a bit easier to understand. But essentially, the way we check sorted, right, and we did this with the previous questions in a rotated sorted array as well. Keep in mind that they are unique in the sense that there will be no duplicates, so there's no flat point essentially. And like I said, so nums L is less than or equal to nums mid. That means that portion of the array sorted, the left portion, right, is sorted in this way. And now we will just check, what does our target actually exist within that particular range of values. If it does, we are happy to go that way, and we would now reduce our binary search to be restricted to that. So R equals to mid minus 1, right? We are only considering the left portion now. If it is not though, then we'll go back to the other side, because we know that we won't find it on this side, so we will go to the other side instead, right? Regardless of the fact that, hey, it is unsorted, right? Like I said, hey, that may be unsorted, but what do? We go and calculate mid back again, right? And eventually we land on a spot where we might have our target within bounds, and we would go there, right? Now the next condition, if the left portion is not sorted, let's check for the right portion. I mean, this is it will be either left or right, right? It can be both. If it is both, we would go into this first, right? And then we would decide, we would already determine where to go with that. But this is the case where it's either left or right, and there's no cases of both of them not being sorted. because it is a rotated sorted array. You can try any sort of combination. You'll see that it comes down to either one of them being unsorted or both being sorted. So our right portion is sorted with this statement. Let's check if it is in bounds. If it is in bounds, then we are happy to check the right portion. And how do you go to the right portion? Oh, L is mid plus 1. If it is not in that portion, then we'll go back to the other half. And at the end of all of this, if you don't find anything, then like any other binary search, just return -1. And that's